Hello again. A common problem facing testers is how they test their software and systems on different architectural choices like operating systems, browsers and so on. And people have found that the all pairs or pairwise test technique is often helpful in reducing the number of combinations they need to cover. Now the CA-ARD optimizer provides all pairs capability, so in this video I'm going to explain what all pairs actually means and also demonstrate how all pairs can be used in ARD to deliver a configuration test. So in this video I want to sort of talk a little bit about testing combinations at scale, which is a challenge once we have lots of variables and values in combination. I'll describe the thinking behind the all pairs technique as a technique and look at configuration testing as a particular example of how all pairs can be useful to us. And then we'll look at ARD itself to model a configuration test, and I'll derive some conclusions at the end. Now, testing combinations at scale has always been our problem in that we know every system has in principle an infinite number of paths. And these paths are derived from the number of combinations and permutations of values that influence the decision making internal to the software. So for example, in an insurance premium calculation, there might be 20, 30 or maybe 50 different pieces of information used to calculate the premium itself. We know when we're testing systems that are going to be used on a range of hardware configurations and software configurations, we should pay attention to this and test these combinations in as realistic a way as we can. But the number of combinations is so huge, we can't possibly do that with physical hardware. Even simple screens for inputs of data onto mobile applications or web pages, we know even simple screens have multiple choices with drop-down lists, radio buttons, checkboxes, and then the validity or otherwise of other data. All this data taken in combination influences the behavior of the system behind the scenes. So we know combinations can be huge in number, and yet we have this challenge of how do we test a subset if we can't test all combination? Now what we know from our use of ARD is that we know already that all paths, all combinations might be out of the question for a realistic size system. And if we select all edges, that is, we cover all the values that our variables can take, this might be more manageable, but then sometimes it doesn't feel like it's enough. So we need something in the middle to help us build confidence. Now, all pairs fits the bill quite nicely in that it exists to provide an intermediate level of coverage between all edges and all paths. All pairs testing is also known as pairwise testing, so some people have a different label for it. Let me spend a moment talking about the thinking behind all pairs as a technique. Suppose in your complex model you've chosen one particular path that goes from the start right through to the end point in your model. And the system, let's say, when you run that test, passes that test. What would be your next test case? Well, one way of thinking about how you derive new test cases and over time to create a full covering set would be to change one test value at a time. So let's have a thought experiment and consider this. Suppose you change one thing and then that test causes a failure. Well, then you could probably trace the problem back to the new test value in combination with one or other of the other values in your table of inputs. Now, if the test passes, then you've gained a little confidence that the new value works with all the other test values in that test case, in that example. So what we can say about all pairs is it says this: we should aim to create test cases that cover every test value in combination with every other test value at least once. We pair every test value with every others, and we look for opportunities to cover those coverage items, if you like, in our set of tests. Now this should give us more confidence than just looking at all test values or all edges, if you like, but it won't be as big a job to run all those tests as it would be if we did all combinations, that is, all paths. Now with configuration testing, the challenge is how do we test a set of different configurations to give us confidence that when our system is used in the field, a certain configuration will not trip the system up and cause a problem? So we typically set out the list of different architectural choices that we want to make and use these in combination to come up with a set of tests of configurations that gives us confidence that we've not got a problem with configurations in the field. If we look at this example, you can see we've got 5 choices: a browser, client operating system, database, web server, and the server operating system. How many combinations? Well, it's 5 times 5 times 3 times 3 times 4. That's making 900. And this is probably far too many. There's no way we could set up an environment with 900 different configurations and expect to test them effectively. This is too many. And we also know, actually, some combinations of architectural choices are impossible. For example, IIS does not run on Linux, and SQL Server doesn't run on Linux either. Now, the main challenge of configuration testing is we need to detect incompatibilities across different configurations. So we might know that the system works on the client operating system Windows 10, and we know that it will work on Windows 2012 server. But do we know that that combination of client operating system and server operating system works? This is the challenge we have. So the usual requirement is to test configuration combinations rather than just pick off all the architectural choices one by one and make sure we cover them all. And all pairs guarantees all the architectural combinations are covered. So the number of tests is much reduced, which is really helpful to us, and I want to show you how we can use ARD to model and test the example that I showed you on the previous slide. Okay, so here we are in Agile Designer again. And I'm going to show you a model I created previously to illustrate how we can create a model for a configuration test and use the all pairs optimization to generate a sensible set of test combinations in our testing. So I'm going to use the magic of cut and paste to speed up the process of creating the model. But I'll explain things as we go, and hopefully you'll trust that I've actually done the right thing. So the first element I've created is, if you like, the choice of browser. So I have a multivariable case statement here for the browsers, and you can see there are 5 choices in the element. So now when I've added the client operating system choices, there are 5 choices there, but I've got the 5 browser connections to this element. So let me add the next one. So we have 3 database choices, and you can see the 5 client operating system connections are connecting with the database. Next comes the web server and the server operating system. I've put them all in at once. So you can see what we have now is we have a model which has 5 decisions, and for the first decision we have 5 outcomes, second 5 outcomes, database 3 outcomes, the web server 3 outcomes, and server operating system we've actually got 4. And then that's it from end to end. So in principle we could use this to generate, for example, all paths and therefore all combinations and permutations of configurations to come up with a list of configurations to test. But we know that's going to be a huge number. So one of the things I mentioned in the PowerPoint was there are a couple of architectural constraints which I'm not allowed to implement, which are basically IIS doesn't run on Linux and SQL Server does not run on Linux. So let's look at these constraints and add them to our model. So these are simple kind of challenges here. So you can see that we've got this one: the database SQL Server and the server operating system Linux must not occur together. The web server as IIS and the server operating system Linux again must not occur together. So we have 2 constraints which will limit slightly the potential combinations and permutations. So now let's go into Path Explorer and just see what we get out of this model. So let me just confirm all possible paths is a huge number. We've put a constraint in, but we'll see how much of an impact that's had on our 900 potential combinations. And the number we get is 775, which is pretty huge. So if you can imagine having 775 distinct test environments to run your configuration test on, that doesn't seem very practical. So what I want to show you now is if we looked at all edges, for example, how many combinations would that come up with? And that just generates 5, because we're just going to sort of pick off the combinations of architectural choices row by row, and we can cover every architectural choice in simply 5 tests. So that's obviously inadequate. We need something better than this. And what all pairs will give us is hopefully all the combinations of every architectural choice with each other. We should have sufficient test cases that exercise all the combinations of these architectural choices. That's where we're headed. So let's try the all pairs optimization. And we get 30. Now 30 is still quite a large number, but it's significantly smaller than the 900 we started with. So what I want to suggest is that this is actually quite a complicated set of combinations, and it's very unlikely, even with the best will in the world, that anyone would create 30 distinct test environments and test. So there's almost certainly more compromises to make. But this is a choice outside the testing arena. It's more to do with the architects and the risk analysis that you might do to make selections and choices of which combinations are the most likely. So to summarise, we saw in the example I showed you that configuration testing can benefit from the all pairs approach. But I want to say that all pairs is a good way of selecting tests if you have concerns that there may be interactions between the various choices made in the model. So if you think that the various values selected in your model, in your system, could influence each other or conflict or contrast with each other to create invalid behaviours within the software, perhaps all pairs is a good solution for you. Now, one example where all pairs might be helpful to you would be in an insurance premium calculation. I mentioned this earlier. In these kind of calculations, the outcome, the premium value, is based on many inputs, 10, 20, 30, who knows, different inputs. And there are very complex rules and logic behind each of these calculations. So there's a good chance that one input could influence several of these rules, and so there may be interactions between the rules that are really difficult to predict ahead of time. So it might make more sense to look at all pairs rather than all edges. All edges will cover all the variations in inputs, but all pairs gives you the combinations of inputs paired off in each case. So all pairs could be a better approach in this circumstance, and it might help you in your application if you do have this concern that there are interactions that are hidden from view.